Tonight, we're going to talk about something that will fundamentally change how you see the cosmos. Right now, as you're watching this, galaxies are disappearing from our reach. Not metaphorically, actually disappearing, racing away from us so fast that no matter what technology we develop, no matter how long we wait, we will never, ever reach them. Most of the universe, the vast majority of galaxies, stars, and worlds out there is already gone, permanently beyond our grasp. And it's happening faster every second. By the end of tonight, you're going to understand why the universe we can actually explore is far, far smaller than you ever imagined. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When you look up at the night sky, you're seeing a universe that seems infinite. Billions upon billions of stars scattered across space, stretching in every direction as far as anyone can see. With powerful telescopes, we can detect galaxies billions of light years away, each one containing hundreds of billions of stars. The numbers become almost meaningless because they're so large. But here's what most people don't realize. We're not just looking at a vast universe. We're looking at a shrinking one. A universe where the boundaries of what we can potentially reach are getting smaller with each passing moment. And the cruel physics behind this shrinkage means that right now, today, we've already lost access to the overwhelming majority of everything that exists. Let's start with what the universe actually looks like on the largest scale. When astronomers map the distribution of galaxies across space, they don't see randomness, they see structure. Galaxies cluster together into groups held by mutual gravity. Our Milky Way is part of the local group, a collection of more than 50 galaxies dominated by three large spirals: the Milky Way, Andromeda, and Triangulum. The local group stretches about 10 million light-years across. That's approximately 60 quintillion miles, or 96 quintillion kilometers. Beyond the local group, you find larger structures, galaxy clusters containing hundreds or thousands of galaxies. Then superclusters, chains and sheets of galaxy clusters stretching across hundreds of millions of light-years. Our local group is part of the Virgo supercluster, a massive structure containing thousands of galaxies. And the Virgo supercluster is itself just one small part of an even larger structure called Laniakea, which contains about 100,000 galaxies. Between these structures are voids, vast empty regions containing very few galaxies. The universe looks like a cosmic web, with galaxies concentrated along filaments and sheets surrounding empty voids. This structure formed over billions of years as gravity pulled matter together, while the expansion of space stretched the distances between clusters. Now here's where things get interesting, and where the problem begins. The universe is expanding. Not expanding into anything, but rather space itself is stretching. Every point in space is getting farther from every other point. This expansion was discovered in the 1920s by astronomer Edwin Hubble, who noticed that distant galaxies are all moving away from us. The farther away a galaxy is, the faster it's receding. This relationship is perfectly linear. A galaxy twice as far away recedes twice as fast. A galaxy 10 times farther recedes 10 times faster. This is called Hubble's law, and it reveals something profound about the nature of space itself. The recession isn't because galaxies are moving through space away from us. It's because space between us and those galaxies is expanding, carrying them along. Understanding how Hubble figured this out requires knowing a bit of history. In the early 1900s, most astronomers thought the Milky Way was the entire universe. They saw fuzzy patches of light, called nebulae, scattered across the sky, but assumed these were gas clouds within our own galaxy. The idea that there might be other galaxies beyond the Milky Way was controversial. Some astronomers suspected those fuzzy nebulae were actually distant island universes, as they were called then, but there was no way to prove it. The distances were too great to measure. Everything changed in the 1920s. Hubble, working with the newly completed 100-inch telescope at Mount Wilson Observatory in California, the largest telescope in the world at the time, made observations that revolutionized our understanding of the cosmos. He focused on a nebula called Andromeda, which appeared as a faint smudge of light in the constellation of the same name. Within Andromeda, Hubble identified individual stars. Not just any stars, but a specific type called Cepheid variables. These stars pulsate, brightening, and dimming with a regular period. And here's the key. Their period of pulsation is directly related to their intrinsic brightness. A Cepheid that pulsates every 10 days is intrinsically brighter than one that pulsates every 5 days. This relationship, called the period luminosity relationship, had been discovered by astronomer Henrietta Leavitt in 1912. By measuring how bright a Cepheid appears and knowing how bright it actually is based on its pulsation period, you can calculate its distance. It's like knowing that a standard light bulb is always 100 watts. If you see one that looks dim, it must be far away. If it looks bright, it must be nearby. Hubble measured Cepheids in Andromeda and calculated their distance. The result shocked the astronomical community. Andromeda was nearly 1 million light-years away, far, far beyond the edge of the Milky Way. It wasn't a nebula within our galaxy. It was an entirely separate galaxy, comparable in size to the Milky Way itself. Overnight, the universe became vastly larger. Other fuzzy nebulae were identified as galaxies too, millions of them scattered across space. The Milky Way went from being the entire universe to being just one galaxy among countless others. But Hubble didn't stop there. He began measuring the distances to many galaxies using Cepheid variables and other techniques. And he also measured something else, the spectra of those galaxies. When you pass light through a prism or a diffraction grating, it spreads out into a spectrum, a rainbow of colors. Within that spectrum are dark lines at specific wavelengths. These lines are absorption features, where elements in the star's atmosphere absorb light at characteristic wavelengths. Every element has a unique fingerprint of absorption lines. Hydrogen creates lines at specific wavelengths. Calcium creates different lines. By looking at these spectral lines, astronomers can determine what elements are present in a distant object. But Hubble noticed something odd. The spectral lines from distant galaxies weren't at the wavelengths they should be. They were shifted toward longer wavelengths, toward the red end of the spectrum. This is called redshift. Redshift occurs when the source of light is moving away from you. It's the Doppler effect, the same phenomenon that causes an ambulance siren to sound different as it approaches and then recedes. As the ambulance approaches, sound waves bunch up, increasing the frequency, making the pitch higher. As it recedes, sound waves stretch out, decreasing the frequency, making the pitch lower. Light works the same way. If a galaxy is moving away from you, the light waves stretch, shifting toward longer wavelengths, toward red. If it's moving toward you, the waves compress, shifting toward shorter wavelengths, toward blue. Hubble measured the redshift of dozens of galaxies, and he noticed a pattern. The farther away a galaxy was, the more redshifted its light. Distant galaxies were receding faster than nearby galaxies. In 1929, Hubble published his findings. The relationship between distance and recession velocity was linear. Double the distance, double the recession speed. This became known as Hubble's law, though the relationship was actually predicted by Belgian astronomer Georges Lemaitre a few years earlier, based on Einstein's equations of general relativity. Lemaitre had proposed that the universe was expanding, but his work was published in a less-read journal and didn't get as much attention. Hubble's observations confirmed the prediction. The universe is not static. It's expanding. At first, this seems counterintuitive. If all galaxies are moving away from us, doesn't that put us at the center of the universe? No. Here's why. Imagine you're an ant on the surface of a balloon. As the balloon inflates, the rubber surface expands. Every ant on the surface sees every other ant moving away. An ant on one side of the balloon looks around and sees all other ants receding. An ant on the opposite side sees the same thing. There's no center on the surface of the balloon. Every point is equivalent. Every ant thinks it's at the center because everything is moving away from it. But the expansion isn't happening from any particular location. The entire surface is expanding uniformly. That's what's happening with the universe. Space itself is expanding uniformly. Every galaxy sees every other galaxy receding. There's no center to the expansion, no special location. It's a property of space itself, not of any particular location within space. This is hard to visualize because we're embedded in the universe. We can't step outside and look at it from an external perspective, the way we can look at a balloon. But the mathematics is clear. General relativity, Einstein's theory of gravity and space-time, predicts that a universe filled with matter and energy should either expand or contract. It can't remain static. Einstein initially added a term called the cosmological constant to his equations to force a static solution, because he, like everyone else at the time, assumed the universe was unchanging. When Hubble's observations showed the universe was expanding, Einstein called the cosmological constant his biggest blunder. Though, ironically, it turns out the cosmological constant, or something very much like it, actually does exist. We call it dark energy now, and it's causing the expansion to accelerate. But we'll get to that. Now, if the universe is expanding, that means in the past it was smaller. Keep going back in time, and it gets smaller and smaller. Eventually, you reach a point where all the matter and energy in the universe was compressed into an incredibly tiny, incredibly hot, incredibly dense state. This is what we call the Big Bang, though that name is somewhat misleading. It wasn't an explosion in space. It was the expansion of space itself from an initial state. The Big Bang happened everywhere, simultaneously. Every point in space was once compressed together. When expansion began roughly 13.8 billion years ago, space started stretching, carrying matter and energy with it. As space expanded, matter and energy cooled. In the first moments, the universe was a soup of fundamental particles and radiation, far too hot for atoms to form. Electrons, protons, neutrons, and photons all bounced around in a dense plasma. As expansion continued and temperature dropped, protons and neutrons combined to form the first atomic nuclei during the first few minutes. This is called Big Bang nucleosynthesis. It produced hydrogen and helium nuclei in ratios that match what we observe in the universe today. About 75% hydrogen, 25% helium by mass. This agreement between prediction and observation is one of the strongest pieces of evidence for the Big Bang. But even after nuclei formed, the universe was still too hot for atoms. Free electrons scattered photons constantly. Light couldn't travel far without bouncing off an electron. The universe was opaque, like a dense fog. This continued for about 380,000 years. Then, finally, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. This is called recombination, though that's a misleading name because it wasn't recombination, it was the first time atoms formed. Once atoms formed, photons could travel freely. They no longer scattered off free electrons because the electrons were bound up in atoms. The universe became transparent. Those photons, from the moment of recombination, have been traveling through space ever since. As space expanded, the wavelengths of those photons stretched. They started as visible light, but over billions of years of expansion, they've been redshifted into the microwave part of the spectrum. Today, we detect them as the cosmic microwave background radiation. It's the afterglow of the Big Bang, photons that have been traveling through space for over 13 billion years. The cosmic microwave background was predicted in the 1940s by physicists George Gamow, Ralph Alpher, and Robert Herman. If the Big Bang happened, they reasoned, there should be leftover radiation from that early hot state. And as the universe expanded, that radiation should have cooled and redshifted to microwave wavelengths. They even predicted the temperature it should have. About 5 Kelvin, which is minus 451 degrees Fahrenheit or minus 268 degrees Celsius. The prediction was largely forgotten until 1964, when two scientists at Bell Labs, Arno Penzias and Robert Wilson, were testing a sensitive microwave antenna. They kept detecting a persistent noise that seemed to come from every direction in the sky. No matter where they pointed the antenna, the signal was there. At first, they thought it was interference, maybe from pigeons nesting in the antenna. They cleaned out the antenna, getting rid of what Penzias later diplomatically called a white dielectric material, also known as pigeon droppings. The signal didn't go away. They checked their equipment thoroughly. The signal persisted. Eventually, they learned about the theoretical prediction and realized they had discovered the cosmic microwave background. The temperature they measured was about 3 Kelvin, which is minus 454 degrees Fahrenheit or minus 270 degrees Celsius, close to the predicted value. The small difference came from refinements in the theory and better observations. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their discovery. The cosmic microwave background is one of the most important pieces of evidence for the Big Bang. It's direct observation of the early universe, photons that have been traveling for over 13 billion years. By studying tiny variations in the temperature of the cosmic microwave background, astronomers can learn about conditions in the early universe. These tiny fluctuations, variations of only a few parts in 100,000, represent the seeds that eventually grew into galaxies and galaxy clusters. Slightly denser regions in the early universe had slightly stronger gravity. They attracted more matter. As the universe expanded, these regions continued to attract matter, growing denser while surrounding regions became more empty. Eventually, after hundreds of millions of years, the overdense regions collapsed to form the first stars and galaxies. The pattern of fluctuations in the cosmic microwave background matches the distribution of galaxies we see today. It's a direct link between the universe at 380,000 years old and the universe at 13.8 billion years old. All of this, the expansion, the Big Bang, the cosmic microwave background, gives us a detailed picture of cosmic history. We know how old the universe is. We know what it was like at different times in the past. We know the composition. About 68% dark energy, 27% dark matter, and 5% normal matter. We know how structure formed, how galaxies evolved, how stars came into existence. But all of this knowledge exists within the framework of an expanding universe. And that expansion has consequences. Profound consequences for what we can and cannot access. The expansion creates a horizon, a boundary beyond which we can never observe anything, because the expansion is carrying those regions away faster than their light can reach us. This boundary is called the cosmological horizon, or sometimes the particle horizon. Currently, it sits at about 46.5 billion light-years away. That's the radius of the observable universe. Everything beyond that distance is permanently invisible to us because light from those regions hasn't had time to reach us yet, and given the expansion rate, it never will. The observable universe contains everything we can possibly see, everything whose light has reached us in the roughly 13.8 billion years since the Big Bang. But here's the thing. Observable doesn't mean reachable. Let me explain this carefully, because it's absolutely critical to understanding why most of the universe is lost. The cosmological horizon marks the edge of what we can observe. But there's a different, smaller boundary that marks the edge of what we could potentially reach, even if we could travel at the speed of light. This boundary is called the cosmic event horizon, and it's already much, much closer than the cosmological horizon. The cosmic event horizon marks the farthest distance we could possibly travel to, even if we left today at the speed of light and kept going forever. Currently, this horizon sits at about 16 billion light-years away. That's roughly 100 quintillion miles, or about 150 quintillion kilometers. Any galaxy beyond 16 billion light-years is already unreachable. If you got into a spaceship right now and accelerated instantly to the speed of light, heading toward one of those distant galaxies, you would never reach it. Never. Space is expanding too fast. Despite traveling at light speed, covering about 5.88 trillion miles, or 9.46 trillion kilometers, every year, the galaxy would keep receding faster than you can catch up. You'd be like someone running up an escalator that's going down faster than you can run. You make progress relative to the step you're standing on, but you're still moving backward relative to the floor. And here's the truly heartbreaking part. This horizon is shrinking. Every second that passes, more galaxies cross the cosmic event horizon and become permanently unreachable. And the numbers are staggering. Right now, about 60,000 galaxies per second are crossing the cosmic event horizon and becoming permanently unreachable. 60,000 galaxies, every single second. Each one containing hundreds of billions of stars, each potentially harboring countless planets. All of them gone forever from our possible reach. Let's put this in perspective. Right now, we can observe about 2 trillion galaxies in the observable universe. That number might actually be higher because many distant galaxies are too faint for our current telescopes to detect. But let's use 2 trillion as our estimate. How many of those 2 trillion galaxies are still within the cosmic event horizon? How many could we theoretically reach if we left today traveling at light speed? The answer is roughly 200 billion galaxies. That's only about 10% of the observable universe. 90% of the galaxies we can currently see are already beyond our reach. They're visible because their light, emitted billions of years ago when they were closer, has reached us. But they've since receded beyond the point where we could ever travel to them. They exist in our past light cone, the set of events that can send light to us, but outside our future light cone, the set of events we could potentially influence or reach. And that 200 billion accessible galaxies, that number is shrinking. Constantly. As we speak, the boundary of the reachable universe is contracting. Eventually, only the local group will remain within reach. Everything else will have receded beyond the cosmic event horizon. Our local group of galaxies, the cluster containing the Milky Way, Andromeda, Triangulum, and about 50 smaller galaxies, will remain gravitationally bound. The gravity within the local group is strong enough to overcome the cosmic expansion. These galaxies will eventually merge together over the next few billion years, probably forming a single large elliptical galaxy. But everything beyond the local group is moving away. The Virgo cluster, despite being relatively nearby, at about 54 million light-years, is already receding. The gravity between the Virgo cluster and our local group isn't strong enough to pull us together. The expansion wins. Over billions of years, the Virgo cluster will recede farther and farther, eventually crossing the cosmic event horizon and becoming unreachable. The same fate awaits every galaxy cluster beyond our local group. The Coma cluster, the Fornax cluster, the Perseus cluster, all the vast structures we can currently observe, all will recede and eventually disappear beyond our reach. So why is this happening? Why is the cosmic event horizon shrinking? The answer lies in something we discovered only recently, something that fundamentally changed our understanding of the universe's fate. The expansion of the universe isn't just continuing, it's accelerating. This acceleration was discovered in the late 1990s when astronomers studied distant supernovae. They expected to find that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. Distant galaxies were farther away than expected, meaning the expansion rate was increasing over time. This discovery won the Nobel Prize in Physics in 2011. The cause of this acceleration is something we call dark energy, though that name is really just a placeholder for our ignorance. We don't know what dark energy is. We just know that it exists because we can see its effects. Let me tell you how this discovery happened, because it's one of the most important scientific findings of the last century. Two independent teams of astronomers were studying distant supernovae in the late 1990s. One team, the Supernova Cosmology Project, was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other team, the High Z Supernova Search Team, was led by Brian Schmidt and included Adam Rees. Both teams were trying to measure the deceleration of the universe. Everyone expected the expansion to be slowing down. Gravity, from all the matter in the universe, should act like a brake on expansion. The question was, how much deceleration? If there was enough matter, the deceleration might be strong enough to eventually stop the expansion and reverse it, causing the universe to collapse in a big crunch. If there wasn't enough matter, the expansion would continue forever, gradually slowing but never stopping. Determining which scenario was correct required measuring the expansion rate at different times in cosmic history. You need to compare how fast the universe was expanding in the past versus how fast it's expanding now. If it's expanding slower now, the universe is decelerating. If it's expanding faster now, that would mean acceleration. But nobody expected acceleration. There was no theoretical reason for it. Expansion should slow down, not speed up. To measure expansion at different times, the teams used Type Ia supernovae as standard candles. These are exploding white dwarf stars. A white dwarf in a binary system can accumulate matter from its companion star. As matter piles up, the white dwarf's mass increases. When it reaches about 1.4 times the mass of the Sun, a threshold called the Chandrasekhar limit, the pressure and temperature in the core become high enough to ignite runaway carbon fusion. The entire star detonates in a thermonuclear explosion. Because all Type Ia supernovae explode at roughly the same mass, they reach roughly the same peak brightness. This makes them excellent distance indicators. When you see a Type Ia supernova in a distant galaxy, you know how bright it actually is at peak. By comparing that intrinsic brightness to how bright it appears, you can calculate its distance. The farther away it is, the dimmer it looks. It's the same principle used with Cepheid variables, but supernovae are far more luminous. They can be seen billions of light-years away, allowing measurements of truly distant galaxies. Both teams searched for supernovae in distant galaxies, measured their brightness, measured the redshift of their host galaxies to determine recession, velocity, and calculated distances. Then, they compared those distances to what would be expected in different expansion scenarios. If the universe was decelerating, distant supernovae should appear slightly brighter than expected. They'd be closer than they would be in a non-decelerating universe. If the universe was expanding at a constant rate with no deceleration, the supernovae would be at the expected distance. The measurements required incredible precision. You're looking at explosions billions of light-years away, trying to determine if they're a few percent brighter or dimmer than expected. Observational errors could easily swamp the signal. Both teams took extreme care with their measurements. They observed dozens of supernovae. They calibrated their instruments meticulously. They accounted for every possible source of error. And when they analyzed their data, both teams found the same thing. The distant supernovae were dimmer than expected. Not brighter, dimmer. This meant they were farther away than predicted. The universe in the past was expanding slower than it is now. The expansion was accelerating, not decelerating. At first, both teams doubted their results. Acceleration made no sense. What could cause expansion to speed up? Gravity should slow it down. They checked and rechecked their data, looking for errors. Maybe dust between us and the distant supernovae was dimming their light, making them appear farther away. But dust absorbs blue light more than red light. It would make the supernovae appear redder. The observations didn't show the expected reddening. Maybe distant supernovae were intrinsically dimmer than nearby ones. Maybe supernovae in the early universe had different properties. but detailed analysis of the spectra showed the distant supernovae were the same type as nearby ones. Every check they performed confirmed the result. The universe is accelerating. In 1998, both teams published their findings. The announcement shocked the scientific community. But as other teams made independent measurements, the result was confirmed. The universe is definitely accelerating. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for this discovery. So, what's causing the acceleration? We don't know. We call it dark energy, but that's just a label. It tells us nothing about what it actually is. Theoretically, there are several possibilities. The simplest explanation is that dark energy is Einstein's cosmological constant. Remember how Einstein added a constant term to his equations to keep the universe static? He later called it his biggest blunder. But maybe it wasn't a blunder. Maybe that constant term actually exists, but with a much smaller value than Einstein used. The cosmological constant represents a property of space itself, an energy density inherent to empty space. As space expands, you get more space, and therefore more dark energy. The total amount of dark energy increases as the universe expands. This is different from matter, where the density decreases as space expands, because the same amount of matter gets spread over more volume. Dark energy maintains constant density. More space equals more dark energy. This pushes galaxies apart, accelerating the expansion. Mathematically, the cosmological constant fits the observations well, but it creates a massive theoretical problem. When physicists try to calculate what the vacuum energy density should be based on quantum field theory, they get an answer that's about 10 to the 120th power larger than observed. That's not a typo. 10 to the 120th power. 1 followed by 120 zeros. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in physics. Why is the observed dark energy density so incredibly, absurdly smaller than the theoretical prediction? Nobody knows. Another possibility is that dark energy isn't constant. Maybe it's a dynamic field that changes over time, something called quintessence. If dark energy is a field, it might have varied throughout cosmic history. Maybe it was weaker in the past and is growing stronger now. Or maybe it will weaken in the future. Current observations are consistent with constant dark energy, but they don't rule out slow changes. Future observations might detect such changes, which would help us understand what dark energy actually is. There are also more exotic possibilities. Maybe our understanding of gravity is incomplete. Maybe general relativity breaks down on cosmic scales, and we need a modified theory of gravity. Maybe the acceleration isn't caused by dark energy at all, but by some quirk of how gravity works over vast distances. Proposals like modified Newtonian dynamics, or MOND, suggest changes to gravity on galaxy scales. But these modifications have trouble explaining all the observations. General relativity works extremely well in most situations. The evidence for dark energy is strong. Whatever it is, it makes up about 68% of the total energy content of the universe. Dark energy has a very specific property. Its density appears to be constant throughout space and time. As the universe expands, the volume of space increases, but the density of dark energy doesn't decrease. This means the total amount of dark energy increases as space expands. More space equals more dark energy. Regular matter and dark matter behave differently. As the universe expands, the density of matter decreases because the same amount of matter gets spread across more space. Imagine a box with 10 marbles in it. If you double the size of the box, you still have 10 marbles, but they're spread over twice the volume. The density has halved. That's how matter works in an expanding universe. But dark energy is different. It's more like a property of space itself. Double the volume of space, and you double the amount of dark energy. The density stays constant. So over time, dark energy becomes increasingly dominant. Early in the universe's history, matter dominated. There was a lot of matter compressed into a small volume. The density of matter was very high. Dark energy existed, but its contribution was small compared to matter. Gravity from all that matter worked to slow the expansion. For the first several billion years after the Big Bang, the universe's expansion was decelerating. Gravity acted like a brake. But as the universe expanded, matter density decreased, while dark energy density stayed constant. Eventually, dark energy became dominant enough that its repulsive effect overcame matter's attractive gravity. That transition happened roughly 6 billion years ago, about half the current age of the universe. Before that transition, the expansion was slowing down. After it, the expansion started speeding up. And as time goes on, acceleration increases because dark energy becomes more and more dominant as matter continues to dilute. Think about what this means for a galaxy far away. Right now, space between us and that galaxy is expanding. The galaxy is receding at some velocity determined by its distance. But that recession velocity isn't constant. It's increasing. Next year, the galaxy will be receding slightly faster. The year after, faster still. This acceleration compounds over time. Eventually, the galaxy will be receding faster than light. Not moving through space faster than light, which is impossible, but being carried away by expanding space faster than light can cross that space. And many galaxies are already in that regime. Let me give you some specific examples to make this concrete. The Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years away. Andromeda is actually moving toward us, not away. Local gravity between the Milky Way and Andromeda is strong enough to overcome the cosmic expansion. We're gravitationally bound, and will eventually collide and merge in about 4 billion years. So, Andromeda doesn't participate in the cosmic expansion on a local level. But beyond the local group, expansion dominates. The Triangulum Galaxy, also in the local group, at about 3 million light-years, is gravitationally bound to us too. It might be orbiting the Milky Way and Andromeda system, or it might fall into Andromeda before that galaxy collides with us. Either way, it's part of our gravitationally bound system. But step outside the local group, and things change. The Virgo cluster, a massive collection of over 2,000 galaxies, sits about 54 million light-years away. That's roughly 315 quintillion miles, or about 510 quintillion kilometers. The Virgo cluster is receding from us at approximately 750 miles per second. That's about 1,210 kilometers per second, or roughly 0.4% of the speed of light. Not particularly fast in cosmic terms. But the Virgo cluster is relatively nearby. Go farther, and recession velocities increase. The Coma Cluster, another massive galaxy cluster, sits about 330 million light-years away. That's roughly 1,940 quintillion miles, or about 3,120 quintillion kilometers. It's receding at approximately 4,300 miles per second, or about 6,950 kilometers per second. That's over 2% of light speed. You can see the pattern. Farther objects recede faster. And this is just among relatively nearby galaxy clusters. The most distant galaxies observable by the Hubble Space Telescope are over 13 billion light-years away. These galaxies are so far that we're seeing them as they appeared when the universe was only a few 100 million years old. Their light has been traveling toward us for over 13 billion years. During that time, space has expanded dramatically. The galaxies themselves have been carried farther and farther away by that expansion. Today, those galaxies are not 13 billion light-years away. Due to the expansion during the light travel time, they're now over 30 billion light-years away. And they're receding at several times the speed of light. 3 times light speed. 4 times. Some even faster. This sounds impossible. Relativity says nothing can move faster than light. But that's not being violated here. Relativity limits how fast something can move through space. An object can't accelerate through local space faster than light speed. If you're in a spaceship and you try to accelerate to light speed, physics prevents it. Your mass would increase toward infinity as you approached light speed. You'd need infinite energy to actually reach it. This is a fundamental limit. No object with mass can reach or exceed light speed through space. But that's not what's happening with distant galaxies. They're not moving through space at faster than light speeds. Space between us and them is expanding at a rate such that the total distance increases faster than light. Think of it this way. Imagine 2 ants on a rubber band. The ants can walk along the rubber at some maximum speed, let's say 1 inch per second. That's their speed limit. They can't walk faster than that. Now, someone starts stretching the rubber band at both ends. The ants are still walking at 1 inch per second relative to the rubber they're standing on. But the rubber itself is stretching. If the rubber stretches fast enough, the distance between the ants can increase faster than 1 inch per second, even though neither ant is walking faster than their maximum speed. That's what's happening in the universe. Galaxies aren't moving through space faster than light. But space between galaxies is expanding, and if there's enough distance, the expansion adds up to more than light speed. This doesn't violate relativity, because relativity limits motion through space, not the expansion of space itself. General relativity, Einstein's theory of gravity and space-time, allows for this. In fact, it predicts it. The equations of general relativity describe how space and time respond to matter and energy. In a universe filled with matter and energy, space can expand, and there's no limit on how fast it can expand. Local physics, the laws of motion within a small region of space, still respect the light speed limit. But global effects, like the expansion of the universe as a whole, don't have that restriction. This creates a horizon beyond which we cannot see. If a galaxy is receding faster than light, its light can never reach us. The photons it emits travel toward us at light speed, but space is expanding fast enough that the distance they need to cover increases faster than they can travel. They make progress in their local neighborhood, but overall, they're losing ground. It's like trying to swim upstream in a river that's flowing faster than you can swim. You're swimming forward relative to the water around you, but relative to the shore, you're being swept backward. The photons from these ultra-distant galaxies are in the same situation. They're traveling through space at light speed, but space itself is expanding fast enough that they're being carried away from us faster than they approach. They'll never reach us. This defines the edge of the observable universe, the cosmological horizon. It's currently about 46.5 billion light-years away. Wait, how can we see something 46 billion light-years away if the universe is only 13.8 billion years old? Shouldn't the edge of the observable universe be 13.8 billion light-years away? The distance light could have traveled since the Big Bang. No, because space has been expanding while the light was traveling. When light from those distant regions was emitted, they were much closer to us. Over the billions of years the light has been traveling, space expanded, stretching the distance. So even though the light has been traveling for 13.8 billion years, the source is now much farther than 13.8 billion light-years away. The observable universe has a radius of about 46.5 billion light-years because of this expansion during the light travel time. Everything beyond that is permanently invisible. Its light hasn't reached us yet, and because of the expansion, it never will. That's the cosmological horizon. This acceleration is what's causing the cosmic event horizon to shrink. In a universe with no dark energy, just matter and radiation, the event horizon would grow over time. You'd be able to reach more and more distant galaxies as time passed, assuming you could travel fast enough. But dark energy changes everything. The accelerating expansion means that distant galaxies are receding faster and faster. The cosmic event horizon still expands in terms of distance, but it expands slower than the universe itself, which means galaxies that are currently inside the horizon, galaxies we could theoretically reach, are crossing outside it. This is happening right now, as you watch this. Somewhere, a galaxy that was barely within reach is now gone. A galaxy containing hundreds of billions of stars, potentially harboring life, maybe even intelligent civilizations. Gone. Not destroyed, not annihilated, but removed from our possible future. Receded beyond the boundary of what we could ever reach, even with infinite time and infinite technological advancement within the known laws of physics. This is the price of living in an accelerating universe. This is the consequence of dark energy. The universe is not only expanding, it's expanding in a way that isolates us more and more. Trillions of years in the future, assuming the universe continues expanding and dark energy remains dominant, the night sky will look very different. From Earth, or from wherever our descendants might be, the only visible galaxies will be those in the local group. Everything else will have redshifted into invisibility. Their light stretched to such long wavelengths by the expansion of space that it becomes undetectable. And eventually, even the light from those distant galaxies will stop reaching us entirely as they cross the cosmological horizon. This paints a rather lonely picture of the far future. A single merged galaxy, probably a giant elliptical formed from the collision of the Milky Way, Andromeda, and the other local group members, sitting alone in an expanding void. Any civilization living in that future galaxy would look out at a dark sky. They'd see stars within their own galaxy, sure, but beyond that, nothing. No other galaxies. no evidence that other galaxies even exist. They'd be completely cut off from the rest of the universe, unable to see or reach anything beyond their own island of stars. And here's something even stranger. Those future astronomers would have a hard time figuring out that the universe is expanding at all. Think about it. Right now, we can measure the expansion by observing distant galaxies and seeing their redshift, the stretching of their light toward longer wavelengths. The amount of redshift tells us how fast they're receding. We can trace this back through cosmic history. We can see the cosmic microwave background, radiation from 380,000 years after the Big Bang. We can detect the signatures of Big Bang nucleosynthesis in the abundances of light elements. We can map the large-scale structure of the universe and see how it formed from tiny fluctuations in the early universe. All of this evidence paints a consistent picture. The universe began in a hot, dense state and has been expanding and cooling ever since. But, in the far future, all those distant galaxies will be gone. There won't be anything left to measure redshift for except nearby stars in the same galaxy, and those aren't receding because gravity holds them together. The cosmic microwave background will be redshifted to such long wavelengths that it becomes essentially undetectable. Its temperature, already just 2.7 Kelvin, which is minus 454 degrees Fahrenheit or minus 270 degrees Celsius, will drop towards zero as the universe continues expanding. Eventually, it will be colder than the background temperature of space itself, which is maintained by the integrated light from all stars and galaxies. Once the cosmic microwave background becomes colder than that background, it will be drowned out and become impossible to detect. Future cosmologists would look at the universe and see a static, unchanging galaxy surrounded by darkness. They might measure motions of stars within the galaxy, see rotation and orbital dynamics, but they'd see no evidence of cosmic expansion. No receding galaxies. No cosmic microwave background. No large-scale structure. They might conclude that their galaxy is the entire universe, that nothing exists beyond it. And in a practical sense, they'd be right. For them, the observable universe will consist of just one galaxy. Everything else has been carried beyond the cosmological horizon, forever invisible. They could develop theories of cosmology based on general relativity. Smart physicists among them might predict that a universe with matter should either expand or contract, but they'd have no observational evidence to test which scenario applies to their universe. They might argue about whether the universe is eternal and static or whether it had a beginning. But without the smoking gun evidence we have, the cosmic microwave background and galactic redshifts, they'd struggle to resolve the debate. Some might propose a Big Bang based on theoretical grounds. Others might favor a steady-state, eternal universe. Both sides would have arguments, but neither would have definitive observational proof. This, actually, has profound implications for how lucky we are to live when we do. We exist at a time when the universe is old enough that we can see the cosmic microwave background clearly. Young enough that the cosmic microwave background is still detectable and hasn't been redshifted into oblivion. Old enough that galaxies have formed and the large-scale structure is visible. Young enough that distant galaxies are still within the cosmological horizon and observable. We're in a cosmic sweet spot, a window of time where the universe's history and structure are observable. Civilizations arising much earlier, say 1 billion years after the Big Bang, would see a very different universe. Much younger, many fewer galaxies, much hotter cosmic microwave background, stars just beginning to form in large numbers. The first generation of stars, made only of hydrogen and helium, would still be around. These first stars, called population 3 stars, were probably much more massive than typical stars today. They lived short, violent lives and exploded as supernovae, seeding the universe with the first heavy elements. An early civilization would see a universe very different from ours, more chaotic, more energetic. But they'd also see some things we can't. They'd see population 3 stars directly, something we can only infer from theoretical models. They'd see the first galaxies forming, the initial collapse of dark matter halos, the ignition of the first stars. They'd witness cosmic dawn, the moment when light began to fill the universe. For us, cosmic dawn is ancient history, detectable only through the faintest signals. For them, it would be current events. On the other end of the timeline, civilizations arising much later, trillions of years from now, would see far less. By then, star formation will have mostly ceased. Gas clouds will have been used up, converted into stars, or expelled from galaxies. The remaining stars will be mostly low-mass red dwarfs, which burn slowly and can last trillions of years. But massive stars, the bright blue and white stars that light up galaxies today, will be gone. They burn fast and die young. Without ongoing star formation, there won't be new massive stars to replace them. The universe will be dimmer. Galaxies will fade as their bright stars burn out. And, of course, all the distant galaxies will be gone, carried beyond the cosmological horizon. Future civilizations will see a dark universe with scattered dim stars, the last remnants of a once brilliant cosmos. They'll have to piece together cosmic history from indirect evidence. Maybe they'll find ancient artifacts from earlier civilizations. Maybe they'll discover old records or data archives. Or maybe they'll be completely cut off, with no way to know what came before. This temporal isolation is just as profound as spatial isolation. Just as most of the universe's space is beyond our reach, most of the universe's timeline is beyond different civilizations' ability to observe directly. Early civilizations can't see the late universe. Late civilizations can't see the early universe. We happen to exist at a time when we can see a significant fraction of cosmic history. That's extraordinarily fortunate. This actually raises an interesting question. Are we typical? Most civilizations that arise in the universe, whenever they arise, will find themselves in a certain context. If most civilizations arise early, when the universe is young and star formation is vigorous, then we're unusual for arising relatively late, after over 13 billion years. If most civilizations arise late, when the universe is old and most stars are red dwarfs, then we're early. Or maybe civilizations are spread roughly uniformly across cosmic time, in which case we're fairly typical. This question relates to something called the anthropic principle. The idea is that we can only observe the universe from a location and time where observers like us can exist. We couldn't have arisen in the first few 100 million years after the Big Bang because there hadn't been enough time for heavy elements to form, for planets to exist, for life to evolve. We couldn't arise in the far future after all stars have burned out because there wouldn't be energy sources to support life. So there's a window of time when observers can exist, and we find ourselves within that window, unsurprisingly. But where in that window are we? Early? Late? Middle? This matters for understanding how common life and intelligence might be. If we're early, and most of the universe's habitable timeline is still ahead, then the majority of intelligent civilizations that will ever exist haven't arisen yet. They're in our future. If we're late, and most of the habitable period is behind us, then most civilizations already existed and are now gone. We're living in the aftermath. Current thinking suggests we're somewhere in the middle to early side. Star formation peaked a few billion years ago and has been declining since. The universe is past its prime in terms of producing new stars. But low-mass stars last so long that there's still trillions of years of habitable time ahead. So we might be relatively early compared to when the majority of civilizations could arise. But this is speculative. We don't know how common life is, how often it evolves intelligence, how long civilizations last. Without more data, we can't answer these questions definitively. What we do know is that our position in time gives us a unique view of the cosmos. We can see things that future civilizations won't be able to see. And that's a privilege, but also a responsibility. If we're among the civilizations that can directly observe the Big Bang's afterglow and the large-scale structure of the universe, then we have an opportunity to learn and record that knowledge. Future civilizations might depend on our observations if their own view of the cosmos is limited. Of course, preserving knowledge across billions of years is its own challenge. But the point stands. Our temporal location in cosmic history gives us access to evidence that won't always be available. Let's bring this back to human timescales, because we've been talking about trillions of years, which is so far beyond human comprehension that it becomes abstract. What does this mean for us, here and now, or for any realistic future human civilization? The harsh reality is that interstellar travel, even to nearby stars, is extraordinarily difficult. The nearest star system, Alpha Centauri, is about 4 light-years away, roughly 25 trillion miles, or about 40 trillion kilometers. The fastest spacecraft we've ever built, the Parker Solar Probe, travels at about 120 miles per second, or about 193 kilometers per second. At its peak velocity when it makes close passes by the Sun. At that speed, reaching Alpha Centauri would take about 6,700 years. That's longer than all of recorded human history. All of civilization, from the first cities in Mesopotamia to today, is less time than it would take the Parker Solar Probe to reach the nearest star, and that's to the nearest star. Most stars are much farther away. The average distance between stars in our region of the Milky Way is about 5 light-years. That's roughly 29 trillion miles, or about 47 trillion kilometers. And that's just average spacing in our relatively sparse neighborhood. In denser regions toward the galactic core, stars are closer together. In sparser regions, they're farther apart. But even in the densest regions, the distances are immense by human standards. Now, the Parker Solar Probe wasn't designed for interstellar travel. It was designed to study the Sun's outer atmosphere by making extremely close passes. Its high velocity is achieved by falling toward the Sun and using gravitational assists. But even if we built a spacecraft specifically designed for interstellar travel, reaching even a small fraction of light speed is incredibly difficult. The problem is energy. To accelerate a spacecraft to high velocity requires energy. A lot of energy. The kinetic energy of a moving object is 1/2 times mass times velocity squared. That squared term is crucial. Double the velocity, and you need 4 times the energy. 10 times the velocity, 100 times the energy. To reach 10% of light speed, which is about 18,600 miles per second, or about 30,000 kilometers per second, you need enormous amounts of energy. Let's do some rough calculations. Suppose you want to send a relatively small spacecraft, say 1,000 kilograms, which is about the mass of a small car, to 10% of light speed. 1/10 of light speed is about 30 million meters per second. The kinetic energy would be 1/2 times 1,000 kilograms times 30 million meters per second squared. That works out to about 4.5 times 10 to the 20th power joules. To put that in perspective, the total world energy consumption for an entire year is about 6 times 10 to the 20th joules. So, accelerating a 1-ton spacecraft to 10% of light speed requires energy comparable to what all of humanity uses in a year. And that's just to get it up to speed. You haven't accounted for the energy needed to carry the fuel, or the inefficiencies of the propulsion system, or any payload beyond the bare spacecraft. Realistic missions would require far more energy. Different propulsion concepts have been proposed. Chemical rockets, the kind we use today, are completely inadequate. The energy density of chemical fuels is far too low. You'd need more fuel than could possibly be carried. The rocket equation, derived by Konstantin Tsiolkovsky in the early 1900s, describes how much fuel you need based on the exhaust velocity of your propulsion system. For chemical rockets, the exhaust velocity is a few miles per second. To reach a final velocity much higher than your exhaust velocity requires exponentially more fuel. To reach 18,600 miles per second with an exhaust velocity of a few miles per second would require a fuel mass exponentially larger than the payload mass. We're talking ratios of millions or billions to 1. Completely impractical. Nuclear propulsion offers better performance. Nuclear fusion or fission could provide much higher energy density than chemical reactions. Proposed designs like nuclear pulse propulsion, where small nuclear bombs are detonated behind the spacecraft to push it forward, could potentially reach a few percent of light speed. Project Orion, a serious proposal from the 1950s and 60s, examined this concept. The idea was to drop nuclear bombs behind the spacecraft and ride the explosion. A large pusher plate would absorb the blast, and shock absorbers would smooth out the acceleration. Calculations suggested it could work. A large Orion spacecraft might reach a few percent of light speed. But it would require thousands of nuclear bombs, massive engineering, and would violate the nuclear test ban treaties that were established in the 1960s. The project was never built. More advanced nuclear propulsion, like fusion rockets, could potentially do better. If you could achieve controlled nuclear fusion, fusing hydrogen into helium and directing the exhaust out the back, you could get exhaust velocities of a few percent of light speed. That's vastly better than chemical rockets. With fusion propulsion, reaching 10% of light speed might be feasible. But controlled fusion remains an unsolved engineering problem. We've been working on it for decades and still haven't achieved sustained net energy gain in a fusion reactor, let alone built a compact fusion rocket. Another concept is antimatter propulsion. When matter and antimatter meet, they annihilate completely, converting all their mass into energy. According to Einstein's equation, E equals mc squared. This is the most energy-dense fuel possible. A few kilograms of antimatter, annihilating with a few kilograms of matter, would release enormous energy. In principle, antimatter rockets could reach very high velocities, maybe 20 or 30% of light speed or even more. The problem is getting the antimatter. Antimatter doesn't exist naturally in any significant quantity. You have to make it in particle accelerators. And the process is incredibly inefficient. You put in far more energy than you get back in the form of antimatter mass. Current production rates are tiny. We produce antiprotons and positrons in small numbers for physics experiments. The total amount of antimatter ever produced by humanity is measured in nanograms. To fuel an antimatter rocket would require kilograms or tons. At current production rates, it would take millions or billions of years to accumulate that much. And even if we could make it, storing antimatter is incredibly difficult. It annihilates instantly on contact with normal matter. You'd need some kind of magnetic confinement system to keep it suspended without touching the container walls. Any failure would be catastrophic. An instant release of all that energy. More exotic concepts include laser sail propulsion. The idea is to build a large, lightweight sail made of highly reflective material. Then you shine an enormously powerful laser at it from Earth, or from a space-based laser array. The photons from the laser bounce off the sail, transferring momentum. This accelerates the spacecraft. Because the laser stays behind and doesn't need to be carried, you avoid the rocket equation problem. You're not limited by fuel mass. The spacecraft can be very lightweight, just the sail and a minimal payload. With a powerful enough laser and a large enough sail, you could potentially accelerate to a significant fraction of light speed. The Breakthrough Starshot initiative, funded by Russian billionaire Yuri Milner and supported by physicist Stephen Hawking before his passing, proposed exactly this. The plan is to build a ground-based or space-based laser array capable of focusing a beam on a small lightweight sail carrying a gram-scale probe. If you could focus enough power, you might accelerate the probe to 20% of light speed or more. At that velocity, it could reach Alpha Centauri in about 20 years. The challenges are immense. You need a laser with gigawatts or terawatts of power. You need to focus that beam over distances of light years without it dispersing. You need a sail that can withstand the intense laser light without vaporizing. You need miniaturized electronics that can survive the acceleration and operate in deep space for decades. And you need a way to send data back, which requires a communication system on a gram-scale probe that can transmit across light years. All of these are currently beyond our technology, but none violate fundamental physics. It's an engineering challenge, not a physics impossibility. Maybe in the coming decades or centuries, we'll develop the technology to make it work. But even if Breakthrough Starshot succeeds, it would only send tiny probes, not humans. Sending people to other stars is orders of magnitude harder. A human mission would require life support, radiation shielding, living space, food, water, air recycling, medical facilities, and enough mass to protect against the hazards of interstellar space. You're looking at a spacecraft massing hundreds or thousands of tons at minimum. Accelerating that to even 10% of light speed would require staggering amounts of energy. And then there's time. Even at 10% of light speed, a trip to Alpha Centauri takes over 40 years. That's a significant fraction of a human lifetime. You'd need a multi-generational crew or some form of suspended animation. Suspended animation remains science fiction. We can cool down and preserve small organisms, but reviving a frozen human is far beyond current medical technology. So you'd likely need a generation ship, a self-sustaining spacecraft where people live, reproduce, and raise children during the journey. The initial crew would grow old and pass away. Their children and grandchildren would continue the voyage. The people who arrive at the destination would be generations removed from those who left. This creates enormous social and psychological challenges. How do you maintain morale and purpose over decades? How do you govern such a society? What happens if internal conflicts arise? These aren't engineering problems, they're human problems. And they're just as difficult. And remember, all of this is to reach the nearest star. Beyond Alpha Centauri, distances scale up. Sirius, the brightest star in our night sky, is about 8.6 light-years away. Vega is about 25 light-years away. The Pleiades star cluster is about 440 light-years away. The galactic center is about 26,000 light-years away. Andromeda is 2.5 million light-years away. Each step up in distance makes the journey exponentially more challenging. Reaching Andromeda at 10% of light speed would take 25 million years. No spacecraft we can imagine would last that long. No civilization would wait that long for results. It's impractical to the point of impossibility. And that's Andromeda, our nearest large galaxy, one of the few galaxies that will remain within reach as the cosmic event horizon shrinks. Galaxies beyond the local group are even farther. The Virgo cluster is 54 million light-years away. At 10% of light speed, over 500 million years. By the time you arrived, the galaxy would have evolved beyond recognition. Stars would have been born and died. Planetary systems would have formed and been disrupted. Any civilization that might have existed there when you left could be long gone. You'd be arriving to a galaxy that's aged 500 million years since you departed. And that's assuming you can even travel at 10% of light speed, which is itself an extraordinary achievement beyond current capabilities. Traveling to other galaxies, even nearby ones like Andromeda, is utterly beyond our current capabilities. Andromeda sits about 2.5 million light-years away, approximately 15 quintillion miles, or about 24 quintillion kilometers. Even traveling at the speed of light, which is physically impossible for anything with mass, the journey would take 2.5 million years. But let's say, hypothetically, that humanity or some other civilization develops the technology to travel at a significant fraction of light speed. Maybe 10% of light speed, which would be an incredible achievement. At that velocity, you could reach Alpha Centauri in about 42 years. You could explore nearby stars within a few decades per trip. Over thousands or millions of years, you could potentially spread across the galaxy, establishing colonies on other star systems, building a true interstellar civilization. Could such a civilization eventually reach other galaxies? Could they escape the local group before those other galaxies recede too far? The answer depends on timing and technology. Andromeda is actually moving toward us, not away. In about 4 billion years, it will collide and merge with the Milky Way. So Andromeda is definitely reachable, though it will come to us rather than us going to it. But what about galaxies outside the local group? Let's take the Virgo cluster as an example. It's currently about 54 million light-years away and receding at roughly 750 miles per second, or about 1,210 kilometers per second. That's about 0.4% of light speed. If you wanted to travel there, you'd need to travel faster than 750 miles per second just to make any progress against the recession. At 10% of light speed, you'd be traveling about 18,640 miles per second, or about 30,000 kilometers per second. That's fast enough to make progress toward Virgo. You'd close the distance, albeit slowly. The journey would take hundreds of millions of years, but it would be theoretically possible. However, there's a problem. The recession velocity isn't constant. It's increasing due to the accelerating expansion. By the time you're halfway to Virgo, several tens of millions of years into the journey, the recession velocity will have increased. The target is accelerating away from you. Eventually, the recession velocity will exceed your travel speed, and you'll start losing ground despite continuing to travel forward. This creates a race against time. For any galaxy outside the local group, there's a window of opportunity to reach it. Early enough, when it hasn't receded too far, and when the recession velocity is still low enough, travel is possible if you have sufficient speed. But wait too long, and the accelerating expansion will make the journey impossible. Even traveling at 99% of light speed, even at 99.99%, eventually the expansion wins. And for the vast majority of galaxies, those billions of light years away, that window has already closed. They're already receding faster than light. The cosmic event horizon has already passed them. They're gone. Permanently. There's another aspect to this that makes the situation even more challenging. Even if you could reach a distant galaxy, what would you find when you got there? Remember, you're traveling for millions or billions of years. During that time, the universe is changing. Stars are being born and dying. Galaxies are evolving. Planets are forming and potentially developing life. But you won't see any of this until you arrive, because information about what's happening can't reach you faster than you're traveling. You'd be heading toward an image of the galaxy as it appeared when you left, but arriving to find a galaxy that's aged millions or billions of years since then. It's like shooting at a moving target through a dense fog where you can't see where the target is now, only where it was minutes or hours ago. Except the time delay is millions of years instead of minutes. Let's think about the philosophical implications of all this. Humans have always wondered if we're alone in the universe. The question of extraterrestrial life has fascinated us for centuries. With modern astronomy revealing billions of galaxies, each containing billions of stars, each potentially hosting planets, the sheer number of possible locations for life seems overwhelming. Surely, somewhere out there, life must exist. Maybe even intelligent, technological civilizations. But if such civilizations exist in distant galaxies, galaxies already beyond the cosmic event horizon, we will never meet them. Never. They could be out there right now, building vast civilizations, creating incredible works of art and science, exploring their own corners of the universe. But we will never know. We will never communicate with them, never share knowledge, never even confirm they exist. The expanding universe guarantees our isolation. Even civilizations in galaxies within our current cosmic event horizon, galaxies we could theoretically reach, present a challenge. If they're in a galaxy 10 million light-years away, any signal they send takes 10 million years to reach us. Our reply takes another 10 million years to reach them. That's a 20 million year round-trip communication time. Civilizations rise and fall in that timescale. Languages evolve beyond recognition. Technology advances in ways we can't predict. The civilization that receives our reply might have no memory of the civilization that sent the original message. They might not even be the same species. And that's for relatively nearby galaxies. For galaxies hundreds of millions of light years away, the communication delay makes any kind of conversation completely impractical. You send a message, and the response comes back hundreds of millions of years later, when humanity might not even exist anymore, when Earth itself might be uninhabitable due to the sun's evolution. The universe is vast, almost beyond comprehension. But the universe we can actually interact with, the region of space we could potentially explore or communicate with, is far smaller, and it's shrinking. Every second, we lose access to thousands of galaxies. Every year, trillions upon trillions of stars slip beyond our reach. The cosmic event horizon is like a retreating shore, and we're watching the ocean of possibilities recede, knowing we can never get it back. This is one of the most sobering discoveries of modern cosmology. We live in an expanding universe, and that expansion has consequences. It means the future is lonelier than we might have hoped. It means most of the cosmos is and will remain forever mysterious to us. It means that the universe we can actually explore is a tiny fraction of what exists. Now, there are some caveats to all of this. First, our understanding of dark energy is incomplete. We observe its effects, the accelerating expansion, but we don't know what causes it. It's possible, though currently no evidence suggests this, that dark energy could change over time. Maybe it will weaken, allowing the expansion to slow or even reverse. Maybe it will strengthen, accelerating the expansion even faster. We don't know. Our models assume dark energy remains constant, but that's an assumption based on current observations, not a proven fundamental law. If dark energy behaves differently in the future, the cosmic event horizon could shift. It might expand, giving us access to more galaxies. Or it might contract even faster, cutting us off from even more of the universe sooner than predicted. Second, we're assuming the laws of physics, as we understand them, remain constant. Relativity limits travel speed to less than light speed for anything with mass. But maybe there are loopholes we haven't discovered yet. Wormholes, hypothetical tunnels through space-time, might allow faster-than-light effective travel by taking shortcuts through higher dimensions. Warp drives theoretical propulsion systems that contract space in front of a ship and expand it behind, might allow apparent faster-than-light travel without actually moving through space faster than light. These ideas are consistent with general relativity under certain conditions, though they require exotic matter with negative energy density, which we've never observed and might not exist. If such technologies are possible, they could change the calculation. Maybe the cosmic event horizon wouldn't be a hard limit after all. But right now, these are purely speculative. We have no evidence they're possible, no idea how to build them, even if they are, and no reason to count on them. Based on physics as we currently understand it, the cosmic event horizon is real, and the universe beyond it is permanently inaccessible. Third, there's the question of what we mean by reach, a distant galaxy. Do we need to physically send people there? Could we send robotic probes instead? Could we send information, encoded in light or other radiation, without sending matter at all? If a civilization just wants to communicate rather than visit, the cosmic event horizon doesn't directly apply. Communication is limited by the cosmological horizon, the edge of the observable universe, not the event horizon. We can receive signals from galaxies far beyond the cosmic event horizon. We just can't send signals that will ever reach them, because they're receding too fast. But we could potentially receive signals from civilizations in those galaxies, signals sent long ago when they were closer. Of course, those civilizations might be long extinct by now. The signal we receive could be billions of years old, a message from a civilization that vanished ages ago, and we could never respond. Our reply would never catch up to them. It would be like finding a message in a bottle washed up on shore from a ship that sank centuries ago. Fascinating, but no possibility of dialogue. So, where does this leave us? What should we make of the fact that most of the universe is already lost? On one level, it's a humbling reminder of our place in the cosmos. We're not just small in space, we're small in accessibility. The overwhelming majority of stars, planets, and possible civilizations are forever beyond our reach. We will never explore them, never know what's there, never meet whatever life might exist there. The universe is far vaster than the portion we could ever hope to touch. This challenges a certain kind of human exceptionalism. We like to think we're important, that we're central to the story of the universe. But the universe doesn't care about us. It expands according to the laws of physics, indifferent to whether anyone wants to explore it. Galaxies recede whether we watch them or not. Dark energy accelerates the expansion, whether we understand it or not. The cosmic event horizon shrinks, whether we like it or not. We're subject to these forces, not in control of them. We can't stop the expansion. We can't prevent galaxies from receding. We can't reach out and grab distant galaxies to keep them from slipping away. We're passengers in an expanding universe, watching the scenery recede into the distance. But there's another way to think about this. The fact that we can understand what's happening is itself remarkable. We're tiny creatures on a small planet. We've existed as a species for only a few 100,000 years. We've had civilization for maybe 10,000 years. We've had modern science for a few centuries. And yet we've figured out the large-scale structure and dynamics of the universe. We know the universe is expanding. We know how old it is. We know what it's made of, at least in broad strokes, even if we don't understand dark matter and dark energy in detail. We can predict the future evolution of the cosmos, billions or trillions of years ahead. We can look back to within fractions of a second after the Big Bang and understand what was happening. That's extraordinary. The universe is comprehensible. And we, despite our limitations, have comprehended significant parts of it. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. We shouldn't be able to understand it. We're evolved primates whose brains developed to handle problems of survival in an African savanna, finding food, avoiding predators, cooperating with tribe members. Our brains weren't designed to grasp quantum mechanics or cosmology or the curvature of space-time. And yet, somehow, they can. Through mathematics, observation, experimentation, and careful reasoning, we've extended our understanding far beyond what our immediate senses can perceive. We've built instruments to see what our eyes cannot, telescopes to gather light from the farthest galaxies, particle accelerators to probe the structure of matter at the smallest scales, gravitational wave detectors to sense ripples in space-time from colliding black holes billions of light-years away. We've developed mathematical frameworks to describe phenomena we can't directly experience. General relativity, quantum mechanics, statistical mechanics, These theories let us make predictions, test them against observations, and refine our understanding. The fact that this works, that the universe follows mathematical laws we can discover and understand, is a profound mystery in itself. But it does work, and that's a reason for optimism, even in the face of cosmic isolation. On another level, the shrinking, accessible universe emphasizes the preciousness of what we do have access to. The local group will remain within reach. Our own galaxy, the Milky Way, contains hundreds of billions of stars. Current estimates put the number at around 200 billion to 400 billion stars. Let's say 200 billion as a conservative estimate. Many of those stars have planets. The Kepler Space Telescope, which operated from 2009 to 2018, discovered thousands of exoplanets. Based on its observations, astronomers estimate that most stars have at least one planet. Many have multiple planets. Some have planets in the habitable zone, the region where liquid water could exist on a planet's surface. If we assume even a conservative estimate, maybe 10% of stars have a potentially habitable planet. That's 20 billion potentially habitable planets in the Milky Way alone. 20 billion. And that's just in our galaxy. The local group contains about 50 galaxies when you count all the dwarf galaxies. The three large spirals, Milky Way, Andromeda, and Triangulum, dominate in terms of stellar mass. Andromeda is slightly larger than the Milky Way, containing perhaps 400 billion stars. Triangulum is smaller, maybe 40 billion stars. The remaining dwarf galaxies contain anywhere from a few million to a few billion stars each. Add it all up, and the local group contains somewhere between 700 billion and 1 trillion stars. Let's say 1 trillion as a round number. If 10% have potentially habitable planets, that's 100 billion habitable worlds within the local group. 100 billion. We have an entire galaxy to explore, even if we never leave it. And exploring even a tiny fraction of the Milky Way would be an achievement beyond anything humanity has yet accomplished. We've sent probes to every planet in our solar system. We've landed on the Moon. We've put rovers on Mars. We've sent Voyager spacecraft beyond the edge of the solar system into interstellar space. But we haven't yet sent a probe to another star. We haven't detected definitive biosignatures on any exoplanet. We haven't found evidence of intelligent life beyond Earth. There's so much still to discover just in our local neighborhood. Within 100 light-years of Earth, there are about 15,000 stars. Most have never been closely examined. We don't know if they have planets. We don't know if any of those planets have life. There could be entire ecosystems, complex biospheres, maybe even technological civilizations within 100 light-years, and we wouldn't know. Our search for extraterrestrial intelligence has barely scratched the surface. We've listened for radio signals from a small fraction of nearby stars. We've looked for optical signals, brief flashes that might indicate laser communication. But our searches have been limited by technology, funding, and time. We've only been seriously searching for a few decades. The universe is billions of years old. We're newcomers to this search. Maybe other civilizations arose millions or billions of years ago and have long since disappeared. Maybe they're out there now, but using communication methods we haven't thought to look for. Maybe they're deliberately quiet, not broadcasting, making them hard to detect. Maybe life is common, but intelligence is rare. Maybe intelligence is common, But technological civilizations are short-lived. We don't know. And we won't know unless we keep looking, keep exploring, keep pushing the boundaries of what's possible. The cosmic event horizon doesn't eliminate wonder. It just focuses it. Instead of wondering about the entire infinite cosmos, we wonder about the accessible cosmos, still vast, still largely unexplored, still full of possibilities. The Milky Way alone offers enough mysteries to occupy humanity for millions of years. How do stars form in detail? We understand the basics, but there are still open questions. How do planetary systems evolve? How common is life? How does intelligence arise? What's the nature of dark matter that holds galaxies together? How do supermassive black holes grow? How do galaxies evolve over time? What happens in the cores of neutron stars where matter is compressed beyond anything we can replicate in laboratories? These questions all have answers waiting to be discovered within our own galaxy. And maybe, if we survive long enough, if we spread throughout our galaxy and build a true interstellar civilization, maybe we'll find that's enough. Maybe the local group will provide everything a civilization could want. Enough stars to explore, enough worlds to inhabit, enough resources to build a thriving society that lasts for billions of years, enough mysteries to investigate, enough beauty to appreciate, enough challenges to overcome. Think about what a Milky Way spanning civilization would look like. Colonies around thousands or millions of stars. Each colony potentially developing its own culture, its own variation on human society. Different worlds with different environments, producing different adaptations, different technologies, different arts and philosophies. A network of star systems connected by trade, communication, shared knowledge, but also independent enough that each develops its own character. Over millions of years, the diversity would be staggering. Humans, or whatever we evolve into, adapted to different gravities, different atmospheres, different stellar types. Some might be biological, others might merge with technology, becoming cyborgs or uploading themselves into computers. Some might remain planet-bound, others might live in space habitats, never setting foot on a planet. The variety of human, or post-human, experience would far exceed anything we've seen on Earth. And all of this within just one galaxy. We wouldn't need other galaxies to have a rich, complex, diverse civilization. The local group gives us about 50 galaxies. Once they've all merged together over the next few billion years, we'll have one large galaxy, sometimes called Milky Way, containing all that matter. Roughly 1 trillion stars. If we could establish a presence throughout Milky Way, that would be an achievement almost beyond imagination. A civilization spanning 1 trillion star systems. Each system potentially harboring billions of people or post-human entities. The total population could be in the quintillions or sextillions. Numbers that make Earth's current 8 billion people seem like a rounding error. And all of those people, or entities, or whatever form life takes in the far future, could be living rich, meaningful lives. Exploring, creating, learning, loving, experiencing existence in ways we can't currently imagine. The shrinking of the cosmic event horizon doesn't prevent that future. It just means that future will be confined to the local group instead of spanning the entire universe. Is that a tragedy? From one perspective, yes. We're losing access to the vast majority of cosmic real estate. But from another perspective, what we keep is more than enough. The local group offers room for essentially unlimited growth and development. We'll never run out of space to explore or resources to use. Not on any timescale relevant to any civilization. So maybe the lesson here is about perspective and acceptance. Acceptance of the limits the universe imposes. We can't change the laws of physics. We can't stop dark energy. We can't prevent the cosmic event horizon from shrinking. These are facts of reality, as immutable as gravity or thermodynamics. Fighting against them is futile, but accepting them doesn't mean giving up. It means focusing on what we can do within those constraints. And what we can do is still extraordinary. We can explore our galaxy. We can search for life on other worlds. We can build a spacefaring civilization. We can spread throughout the local group. We can ensure that Earth life, in whatever form it evolves into, endures for billions of years. We can create art, music, literature, science, philosophy, cultures, and societies beyond anything we've yet imagined. We can leave a legacy that lasts until the stars themselves burn out. That's not nothing. That's a future worth working toward. And there's something almost poetic about boundaries. Without limits, without constraints, everything becomes possible, and therefore, nothing has special value. If we could reach any galaxy, visit any star, access any world, then no particular place would matter more than any other. Everywhere would be equally accessible, equally reachable. But with boundaries, with limits, what's accessible becomes precious. The stars we can reach matter more because we can't reach all stars. The galaxies within our local group matter more because we can't visit galaxies beyond. The time we have to observe the cosmic microwave background matters more because future civilizations won't have that opportunity. Scarcity creates value, and the cosmic event horizon creates cosmic scarcity. It tells us that the universe we can touch is limited, and that makes it precious, worth protecting, worth exploring, worth appreciating, because we can't take it for granted. Because we can't assume there's always more beyond the next horizon. The horizons are closing. What remains is what we have, and we should make the most of it. Consider what exploration means in this context. When ancient human civilizations first ventured beyond their villages, the world seemed infinite, endless horizons, limitless possibilities. But as we explored more, we discovered the world has edges. Oceans we couldn't cross without ships. Mountains too high to climb without equipment. Deserts too vast to traverse without preparation. These boundaries didn't stop exploration. They focused it. They made the reachable world precious. Every island discovered mattered. Every mountain peak conquered became significant. Every new land charted added to human knowledge. The fact that there were limits made the achievements meaningful. The same principle applies to cosmic exploration. Yes, 90% of the universe is beyond our reach, but that makes the 10% we can access infinitely more valuable. Every star system we eventually visit will be an achievement. Every planet we explore will expand our understanding. Every sign of life we discover, if we discover it, will be momentous. The boundaries don't diminish these accomplishments. They enhance them. Each step outward, each new world reached, becomes more precious because we know the frontier has limits. We're not exploring an infinite playground. We're carefully charting a finite but vast domain. And there's something deeply human about working within constraints. Throughout history, our greatest achievements have come not from unlimited resources, but from clever solutions to difficult problems. The Apollo program put humans on the moon with computers less powerful than a modern smartphone. Artists create masterpieces within the constraints of their medium. Scientists make breakthroughs by working around the limitations of their equipment and knowledge. Constraints don't prevent greatness. They often enable it. They force creativity, innovation, and determination. The cosmic event horizon is the ultimate constraint on exploration. It tells us the universe we can touch is limited, and that limitation might be exactly what motivates us to explore it fully. If we could visit any galaxy, we might never visit any. Too many choices, no urgency. But knowing our options are finite might be what drives us to make the most of them. There's also the question of meaning and purpose. What does it mean to explore? Is it about covering the maximum territory, seeing the most things, visiting the most places? Or is it about understanding, experiencing, and appreciating what we encounter? If exploration is about deep understanding rather than shallow coverage, then maybe exploring one galaxy thoroughly is more meaningful than superficially visiting 1,000. Maybe studying one potentially habitable planet in detail teaches us more than quickly scanning 1,000,000. Maybe building a lasting civilization in one region of space is a greater achievement than spreading thinly across vast distances. Quality versus quantity. Depth versus breadth. The cosmic event horizon forces us toward quality and depth. We can't visit everything, so we have to be selective about what we explore and how thoroughly we explore it. And let's not forget the timescales involved. We're talking about a future that extends billions of years. Billions of years of potential exploration, discovery, growth, and development. Even if we're confined to the local group, we have billions of years to explore it. That's roughly 250 times longer than Earth has existed. It's roughly 200 million times longer than human civilization has existed. The amount of time available for exploration and achievement within our accessible universe is so vast that it's almost incomprehensible. Any civilization that lasts even a tiny fraction of that time, say 1,000,000 years, would still have barely scratched the surface of what's possible within the local group. There's no rush. There's no urgency to see everything quickly. We have time. More time than we can meaningfully imagine. And in that time, confined to our small corner of the cosmos, we could still accomplish things that would seem miraculous to us today. Think about what a civilization could achieve in 1,000,000,000 years. 1,000,000,000 years ago on Earth, the most complex life was simple, multicellular organisms. No plants on land. No animals. No brains, no eyes, no anything we'd recognize as complex. Fast forward to today, and we have brains sophisticated enough to understand quantum mechanics and general relativity. We have technology that lets us peer back to the beginning of time and probe the structure of atoms. We've split the atom, sequenced our genome, and begun to understand consciousness. All in the time between then and now. Now, imagine another 1,000,000,000 years into the future. What could we accomplish? What technologies might we develop? What understanding might we achieve? What forms might life take? We can't imagine it, because the gap between now and then is as large as the gap between simple multicellular organisms and modern humans, maybe even larger. And we have multiple billions of years available to us within the local group. Multiple iterations of that kind of transformation. The possibilities are genuinely endless, even within finite space. So when we say most of the universe is lost to us, we need to remember what we're comparing against. Lost compared to what? An infinite universe with infinite possibilities. Sure. But what we have is still so vast, so full of potential, so rich with opportunity, that calling it limited seems almost absurd. It's like someone in a mansion complaining they don't have a palace. Technically true, but missing the point. The mansion is already far more than anyone needs. The local group is already far more than any civilization could fully explore or utilize. And there's one more aspect worth considering. The universe we can reach, limited though it is still more than enough to ensure our survival. If the goal is for Earth-originated life to endure, to spread, to thrive, to evolve, and to experience existence on the longest possible timescales, the local group provides that opportunity. We don't need access to distant galaxies for life to continue. We need stable star systems, potentially habitable planets, and enough time for evolution and civilization to unfold. All of that exists within our reach. The cosmic event horizon doesn't threaten our long-term survival. It just limits our long-term expansion. Those are different things. Survival doesn't require unlimited space. It requires enough space, enough resources, and enough time. And we have all three. Finally, there's something poetic about the idea that the universe gives us exactly what we need. Nothing more, nothing less. Not infinite space, which would be overwhelming and meaningless. Not a single solar system, which would be confining and limiting. But a local group of galaxies, enough to explore for billions of years, enough to host an enormous diversity of worlds and civilizations, enough to ensure survival and enable flourishing, but not so much that it becomes incomprehensible or unmanageable. It's almost as if the universe is perfectly calibrated for beings like us. Of course, that's probably just anthropic reasoning. We observe what we observe because we are the kind of beings who can exist in this kind of universe. If it were different, we might not be here to wonder about it. But still, there's something satisfying about the scale we've been given. Large enough to inspire awe. Small enough to potentially understand and explore. Finite enough to be precious. Vast enough to be eternal. From our perspective, maybe the real message here isn't doom and gloom. Maybe it's about acceptance and appreciation. Acceptance of the limits the universe imposes. Appreciation for what falls within those limits. The cosmic event horizon is a boundary, yes, but boundaries give structure to existence. They define what's possible and what's not. They force us to make choices about where to focus our efforts. Without boundaries, without limits, everything would be equally accessible, equally meaningless. With boundaries, what's accessible becomes precious. What we can reach matters more because we can't reach everything. The stars in our galaxy matter more because we can't visit stars in distant galaxies. The potential life on planets in our local neighborhood matters more because we might never meet life in faraway galaxies. Scarcity creates value, and the cosmic event horizon creates cosmic scarcity. So, Here's my final thought. We live in an accelerating universe. Most of what exists is already beyond our reach and receding further every second. The accessible cosmos is vastly smaller than the total cosmos, and it's shrinking. That's the hard truth. But within that accessible region, there is still wonder, still mystery, still countless worlds to explore, still the possibility of life, intelligence, and civilizations to discover. Still the opportunity to spread throughout our galaxy, to build a future among the stars, to ensure that Earth, life, in whatever form it takes millions or billions of years from now, endures. The universe may be shrinking around us, but what remains is still unimaginably vast. We can mourn what's lost, or we can celebrate what remains. We can despair at the boundaries, or we can explore within them. We can lament the cosmos we'll never see, or we can discover the cosmos we can. The choice, as always, is ours. Thanks for sticking with me through this journey across space and time. The cosmic event horizon may be closing. The universe may be accelerating away from us, and most of everything may already be lost. But tonight, right now, we can still look up at the sky and see those distant galaxies. We can still marvel at the scale of existence. We can still wonder what's out there. And we can still imagine a future where humanity reaches for the stars, exploring as much of the cosmos as physics allows. That future isn't guaranteed, but it's possible. And that possibility, however limited by the expansion of space and the dominance of dark energy, is worth pursuing. Keep looking up. Keep wondering. Keep exploring. The universe may be vast beyond comprehension, but the part we can touch is still out there, waiting.